In this video, we're going to look at another example of volumes by slicing. So the question here is to find the volume of a cap of a sphere whose radius is r and the height of the spherical cap is h. The first step, as usual, is to draw a picture of the solid and a cross-sectional slice. So here we have the solid. You can see that we have our goal is to find the volume of this spherical cap. The height of the spherical cap is h. We're going to draw a two-dimensional version of this solid. So we basically get a circle in the xy plane. And the cross-sectional slice has radius x. It's really important that we realize that the radius of the cross-sectional slice is different than the radius of the sphere. The radius of the sphere is fixed. It doesn't change. Regardless of where you draw it, you have, the radius is always going to be r. Whether you draw it here, everywhere, the radius is r. But the radius of the cross-sectional slice changes. So if we were to draw our slice here, you can see it has a smaller cross-sectional slice. And let's draw a circle. There's a circle. And we're going to add up these cross-sectional slices, and we add them in the direction of the y-axis. Now, another thing that's really important is the limits of integration. So because the cross-sectional slice has a height of h, and the top value here, the top of the sphere, is of course r, let's subtract h from it, and we get r minus h as a lower limit of integration. So we have to integrate from r minus h to r, a of y, dy. These limits of integration are really tricky, but you can reason it out by the fact that the radius of the sphere is r, the height of the cap is h, and always bear in mind that you're in a coordinate system. So everything is measured from the origin. The distance from the origin is r, and the height of the cap is h. So in order to get the coordinate of the starting point, the lower limit of integration, we have to do r minus h. All right. So the cross-sectional slice at height y is a circular disk with radius. Radius is equal to x, where the y value ranges from r minus h to r. The area slice at height y is a circle of radius x. And we know what the area of a circle. Well, the area is pi times radius squared. The radius is x, so pi x squared. This is area as a function of x, is pi x squared. But we need it, of course, to be a function of y. So the key concept is that the area slice at height y is a circular disk with radius x perpendicular to the y-axis. So area slice is perpendicular to the y-axis. So we need to find the cross-sectional slice as a function of y, add up these horizontal circular area slices in the direction of the y-axis. So we have to integrate a of y dy from r minus h to r to find the volume of the spherical cap. All right. Here we've drawn one of these cross-sectional slices with radius x, and we're going to integrate from r minus h to r. All right. So our goal now is to find a formula for the cross-sectional area as a function of y. So the slice area is equal to pi times radius squared. The radius is x. We get pi x squared. But we need this slice area to be a function of y, not x. So need area slice to be a function of y, not x. So let's apply the equation of circle with radius r centered at the origin. And alternatively, you can even use Pythagoras. You can see we got x squared plus y squared equals r squared because we have a right angle triangle. So if we apply the equation of a circle, or using Pythagoras, we get x squared plus y squared is equal to r squared. Isolating for x squared, we get x squared is equal to r squared minus y squared. So the cross-sectional slice area is pi x squared, and x squared, we have solved it in terms of y squared, so we get pi times r squared minus y squared. And now this is a function of y. The cross-sectional area is a function of y, and now it can be added in a direction of the y-axis. It can be integrated with respect to y. So slice area is equal to pi x squared. The circle equation relates x and y. Circle equation x squared plus y squared is equal to r squared. Isolating for x squared, we get x squared is equal to r squared minus y squared. Cross-sectional slice as a function of y. We start with pi x squared. Solving for x squared in terms of y, we get pi times r squared minus y squared. Now that we have found the area slice, a of y, this will form the integrand of the volume formula. The volume formula is integral from c to d, a of y, cross-sectional slice as a function of y, integrate with respect to y. C is a lower y value, lower y limit of integration, which is r minus h. That's this part here, r minus h. D is the upper y limit of integration, d is equal to r. And we've drawn a picture here in this diagram that explains that, because the radius is r, that's the radius of the sphere. The height of the spherical cap is h. So to find a lower limit of integration, we have to subtract h from r and get r minus h. So the cross-sectional slice a of y is equal to pi times x squared, but x squared is equal to r squared minus y squared, where y is between r and r minus h. All right, now we have to do the integration. Integrate the area slice to find volume. The volume is equal to integral from c to d, a of y dy. C is equal to r minus h, d is equal to r, and cross-sectional slice as a function of y is pi times r squared minus y squared. So volume is equal to integral from r minus h, lower limit of integration, to the upper limit r, pi times r squared minus y squared dy, integrating with respect to y. Pi is a constant, passes through the integral, so we get pi integral r minus h to r squared minus y squared dy. So volume is equal to pi. Integrating r squared, we get r squared y minus integrating r squared, we get r squared y, and integrating y squared, reversing the power rule, we get y cubed divided by 3. Evaluated from r minus h to r. Applying fundamental theorem of calculus, putting the upper limit in, we get pi times r cubed minus r cubed over 3 minus r squared times r minus h minus r minus h cubed divided by 3, and then close the bracket and another close the main bracket. All right, so volume is equal to pi times r cubed minus r cubed, simplifying it a bit more, minus, so r squared times r is r cubed, times minus, we get minus r cubed. R squared times h is minus hr squared, we get plus, because minus times minus is plus, plus r squared h, and minus times minus is plus r minus h, all cubed, divided by 3. So the only simplification we can do from this is r cubed minus r cubed, that's gone. So now we want to simplify it more to get a neater answer. So we get pi times r minus h cubed divided by 3 minus r cubed divided by 3 plus r squared h. All right, so what we have is volume is equal to pi times r minus h cubed. Sorry, let me write that as r minus h all cubed divided by 3 minus r cubed divided by 3 plus r squared h divided by 1. Adding these fractions, taking common denominator, we get pi times r minus h cubed minus r cubed plus 3r squared h divided by 3. Basically adding up these fractions. Now, I want to expand this r minus h cubed so we get things canceling out. R minus h cubed, if we were to expand this, we're going to get r cubed minus 3 r squared h plus 3 r h squared minus h cubed. Let's insert this in and simplify. The volume is equal to pi times. We have r cubed minus 3r squared h plus 3r h squared minus h cubed as the expanded version of r minus h cubed minus r cubed plus 3r squared h, all divided by 3. Well, we get more simplification. Now we have another r cubed canceling with r cubed, and we have minus 3r squared h canceling with plus 3r squared h. So there's not much left. What we get is volume is equal to pi times 3r h squared minus h cubed divided by 3. We can factor out h squared because we have a common factor of h squared in these two terms. So we get pi h squared times 3r minus h divided by 3. Well, we can divide by 3 again. We can basically simplify this fraction. We get 3r divided by 3. That's just r minus h over 3. That's the most simplified form for the volume of the spherical cap. Pi h squared times r minus h over 3. Now let's try something interesting. If the height of the cap is equal to radius, we should get the volume of a hemisphere. If we take a look at the picture, for example, there it is, here's the picture here in page 1. If we make the height equal to radius, the volume of the spherical cap should be half the volume of a sphere. Let's test it out. So if we were to substitute h equals r, we'll get volume is equal to pi h squared times r minus r over 3. We get volume is equal to pi h squared times 1 minus 1/3 is 2/3, so we get 2/3 r, and radius is equal, the height is equal to radius, and so we get volume is equal to 2/3 pi, but height is equal to radius. Let's sub it in here as well. We get r cubed. 2/3 pi r cubed is half the volume of a full sphere. The volume of a full sphere is 4/3 pi r cubed. So this was just an extra aside of what would happen if the height of the spherical cap was equal to the radius of the sphere, that is. All right, so in any case, the volume of the spherical cap is this answer here, and then we just did a bit of extra on what would happen if the height was radius. So we substituted h equals r, and we got the volume of a hemisphere, half of a sphere, which is 2/3 pi r cubed. All right, thank you.